So quickly here, let's have a quick look at the handout that I've given you entitled Electric Fields. Okay, so we talked about electric fields a little bit yesterday. This is a lot of the same stuff with a little bit of additional stuff, just sort of a different author. And you can use it as sort of a bit of a review of yesterday and some new ideas as well. So it says, most of the forces we're familiar with in everyday life might be called contact forces. Contact is required between whatever it is that produces the force and whatever it is that receives the force, as when someone pushes on or exerts a force on a lawnmower. If I push on a filing cabinet, there has to be contact, right? I am not Yoda. I cannot push on the filing cabinet simply by doing that. Doesn't work, right? One of these years, I'd like to learn how to do that. Yeah. An electric force, however, is one that acts at a distance. That is, they act even when the bodies involved are not touching. This idea of a force acting at a distance, like we talked about yesterday, is sometimes difficult to understand. So the concept of a field was developed to explain how these forces operate. We talked about that yesterday. We can visualize an electric charge giving rise to an electric field that extends out from the charge and permeates space. So the diagram at the left shows the electric field coming out from the positive charge Q1 in all directions. So I'm just going to quickly draw this. Because it's a positive charge, which way does the field point?
Away.
And does anyone remember why it's away? Evan, do you remember why it's away? If not, you should listen for the answer. A second charge, Q2, would experience a force from Q1 because of the electric field. An electric field is detected with a positive test charge. So we've got little Q2 down here. And it's not marked positive, but you should mark it positive. Q2 is a positive test charge. This elementary positive test charge is placed close to the charged body whose electric field we want to determine. So we use another electric charge to figure out what the field is like of the big one there. The magnitude and the direction of the electric force acting on the positive test charge is the electric field. So because this one is positive, and what would happen to it when it's placed in that electric field? Where would it go?
Away.
It would go away like this, right?
Yep.
So in other words, the force on this is that way, which means the electric field at that point is also away. Also away. Okay? It's important at this point to remember that all forces are vectors. Are you serious? Like 3 feet away. No, I'm not in the mood for jokes.
Good one.
It's important at this point to remember that all forces are vectors and must have a direction associated with them whenever a calculation or description involving a force takes place. And that would be like away or towards or positive or negative. Since the field is a special case involving a force, then it too must be described as a vector. Note that the electric field is directed away from a positively charged point. An electric field is directed away from a positively charged point. You should be following along. As the positive test charge moves closer to the positively charged point, the electric field becomes larger. Okay, if I've got my little red guy here, and if I've got him in there close, what kind of force is going to be on the guy?
Big one.
Bigger. Big force. Because it's close. Yes, that's big. Sort of like Grover. Near. Far. Near. Far. Near. Far. Now, that's because the blue guy, the blue arrow, much like Grover, is a vector. But the black ones, are the black ones vectors? No. The black ones are not vectors. What are they called?
Electric field.
Electric field lines, Mike, right? That's right. Electric field lines. Now, how do we determine the blue guy? If it's small, then that means small electric force, right? If it's big, well, then that means big, right? But the electric field lines don't work that way. The electric field lines don't get bigger and smaller. Adam, how do we determine where the force is strong based on the electric fields? How far apart they are. You'll see way out here, Devin, they are quite a ways apart. In closer, closer together, stronger there. Near, far. Have to remember to put Grover in the notes. Now, in the second one down there, Devin, it says that the electric field points towards a negatively charged object. In any case, the electric field is described as the electric force acting on a single positive test charge. You'll notice down here, the second picture, CQ1 is close, it's got a big arrow. CQ2 way at the bottom? Smaller, farther away. Are those two arrows, are those vectors, or are those field lines? Those are vectors, because they get bigger and smaller. All right. The equation that can be used to determine the electric field when there are two charged objects is E equals F over Q. E equals F over Q. Where E is the electric field measured in newtons per ELCH. Anybody want to take a wild, crazy guess at what ELCH stands for?
Electric.
Very close. It's another word that starts with EL.
Michael.
EL, Michael, not MI.
Electronic or glass. Electrons.
What type of school do you go to when you're grades 1 to 6? Elementary.
Kindergarten.
Elementary, and then the CH? Charge. Elementary charge. So the electric field,
E equals F in.
okay, Devin, take it off. ELCH stands for elementary charge, or newtons per coulomb. Newtons per coulomb. FE is the electric force between two charged points. Now you'll notice that there's no unit there for force. What do we measure force in, Terry? Newtons. So you should indicate newtons there beside FE at the bottom. Q stands for electric charge on the charge point, where the electric field is to be determined in elches, elementary charge, or coulombs. Coulombs of charge. Flip the page over. Some properties of electric fields. Lines of force show the direction that a positive charge would move if placed near the charged object. Thus, lines of force originate at positively charged objects and go towards negatively ones. The direction of the electric field at some point is taken to be the direction of a line drawn tangent to an electric line of force at that point. Number 2 says lines of force are perpendicular to the surface of the conductor. Number 3 says the electric field strength is proportional to the density of the electric lines of force. In other words, when they're close together, they are strong. When they are far apart, they are weak. Electric lines of force never cross one another. The electric field over a charged plane is uniform in magnitude and direction. In other words, the lines are parallel. Very good, Mike. Write that in there on the side. Right there in there on the side in the back. Lines are parallel. Hello.
Are you ready to take your call?
And the last one there, the electric field between the two charged plates is uniform at all points between the plates. You'll notice that once again, the lines are parallel. Okay, so yes, we will be going down to Electric Avenue. Thank you, Devin, for the flashback to the 80s there. You might want to jot some of these down. It's entirely up to you. Okay, an electric field is similar to a gravitational field. Now, there are a few ways how they are similar, and there are a few ways that they are different. Can you give me one way that electric fields and gravitational fields might be similar?
You broke their fields.
Let's expand on that, Hunter. They are fields. What does that mean? They do exert a force, that's true. They take up space, okay. Remember, electric fields, gravitational fields, act at a distance, exactly. Act without contact, that's good. Now, there's one major difference between gravitational fields, Devin, and electric. Riley, please, I need you to listen to this too. One major difference between electric fields and gravitational fields.
Electric fields push out.
And?
Pull.
Gravitational pull.
So gravity only does, and electric fields do push and pull. Electrics can go both ways. Gravity can only pull. Riley, what's the major difference between electric fields and gravitational fields?
Gravitational fields pull.
And?
The other one does everything else. That's both.
Does anybody else want to jot that down?
I will.
That's one of the major differences. Now, a gravitational field is defined as the amount of force exerted upon a unit of mass. Pause there. Okay, so one of them, remember, a gravitational field is defined as the amount of force exerted upon a unit of mass. An electric field would then be same idea, amount of force but exerted upon a unit of. Starts with a C. Unit of, not croutons, no, good guess. Charge. Unit of charge. Okay. Also, gravitational field exists around objects with mass. Large masses like planets have strong gravitational fields. So they're talking here about gravitational fields before they talk about electric fields, right? Here's the bit about electric fields. Around any charged object, there exists an electric field. Objects with a large charge have a strong electric field. These fields are shown by a series of arrows radiating inwards or outwards, and they are called lines of force or field lines. So here's an example of an electric field. Can you tell whether the charge in the middle is positive or negative? Definitely positive. How do we know? Well, it says +1 in there. Arrows are out, right? Exactly. Remember that the closer the lines are, the stronger the field is. So like strong in here, where Grover would say near.
That's strong.
Right?
It's strong.
Out here,
Really weak.
weaker. Now that's actually based on an inverse square law. Have we talked about the inverse square law? Did you talk about inverse square law with gravity?
No.
Yeah.
Yeah?
Yeah.
Inverse square law says that if you're twice as far away, the strength is?
Double.
No.
Double weak.
No.
Double weak.
No. 1/4.
Yeah.
Inverse square. Square. So 3 times as far?
8, 16.
Half.
Thank you, Riley. 1/9.
I said
3 squared. 9. I'll give you another chance. 4 times as far?
12.
16. Thank you, Courtney.
that's so
16. Oh, boy. Yeah. Inverse square law. Actually, I might want to do a lab one of these days on that.
How can we derp so hard?
Inverse square law. Okay. Okay. And here it is. It says right here, if the distance is doubled, the field strength is 1/4. What if it was like, what if the distance wasn't doubled? What if it was like 2.5 times? 2.5 times. How would you do that?
I don't know.
And I don't need a fractional answer. Like how did I get that 1/4? Doubled, 2 squared is? Thank you. So you put it on the bottom. So in other words, instead of doubling 2 times, it would be 2.5. So I'd have to do what? Same process.
Multiply.
Instead of taking 2 squared, I'm going to go
2.5 squared.
2.5 squared. What's 2.5 squared? Anybody know?
5.
2.5 squared is 5.
7.
2.5 times 2.5 is 6.
Definitely 7.
2.5 times 2.5 is 7.
5.
2.5. 2.5. 6.25. Thank you.
2.5.
6.25. I feel like I'm at the desk. To show the direction of the field, we're going to bring a smaller charge, a small positive test charge nearby, and it will be repelled, pushed away. Ooh, repelled. Right? It'll look like this. Okay? Which means that the field line's Devin. I thought you said you were going to be quiet for 15 minutes.
Which means the
That's
field
the first
lines.
time I talked.
Since
I said that.
So burping doesn't count.
You said you weren't going to talk anymore. You're
I
talking
can't help. Just shut up.
Just relax, okay?
I was doing good.
The positive test charge will be repelled, which shows the field lines are
Getting
away. Now, here's an interesting point. And I can't can't move this guy, but if he's in here close, it's going to be a big force, right? And as it moves farther away, the force on it is going to actually
Get weaker.
get weaker. So is it going to continue to move away?
No.
No.
The force on it's going to become less and less, right? Will it? Well, the only way it could stop, remember Newton's law, an object in motion
Stays in motion.
stays in motion. So in fact, what it's going to do is it's going to accelerate really fast at the start, and then as it gets farther away,
Speed.
well, it's going to eventually approach a constant speed, right? The force on it is going to be so small, but it's just going to keep going. Okay. Object with a positive charge that field's a point away. If one were to have a large negatively charged object, then the positive test charge is attracted to it. When the field lines go in,
What happens when it touches the middle?
well, then it would just stick there, right? Because it would be attracted. Yeah. Objects with a negative charge have fields that point toward them. I think we got all this stuff, right? The amount of attraction or repulsion can be used to indicate how strong the electric field is. The field strength is defined as the force the field exerts on a unit of charge. Why did I say it like that?
Right.
The field strength is defined as the force the field exerts on a unit of charge. What do we measure charge in? Anybody remember?
Newton.
No, that's force.
Oh.
Jesse, remember what we measure charge in? Coulombs, that's right, coulombs. Coulombs. So the unit of charge is the coulomb.
Can you teach me how to make
Okay, so we've got E equals F over Q. That's the formula you're going to use. E equals F over Q because Riley, the electric field strength, that's your E, is defined as the force on a unit of charge. That's where the formula comes from. Okay, the electric field strength is, now when I say Fe, what do you think that means?
iron?
Force.
Not iron. Eh,
Electric.
electric force. Electric force. It's the force. What kind of force? It's an electric force. Exactly. E is field intensity or strength, measured in newtons per coulomb. F is the force measured in newtons. Q is the charge in coulombs. Sometimes, is it on this page? Sometimes it would be Elches.
It's a coulomb.
A coulomb is a unit of force. Okay? Now, Elches and coulombs are sort of like millimeters and kilometers, right? They measure the same kind of thing, just they're different sizes. Okay?
Like elk.
All right. Now, positive charges or negative charges? Which ones create stronger electric fields?
Positive.
Positive?
Positive against positive.
You're sure?
I'm pretty wrong then.
The intensity or strength of an electric field is the same for a positive charge as it is for a negative charge. Only the direction is different.
Towards me.
Okay? So it doesn't matter whether it's positive or negative. The strength, the force on it would be the same. Only what would be different?
The direction.
The direction. Only the direction is different.
I'm not hate that. Do I go for Uma? Do I go for a food out? Is he still?
Okay, here is example number one. Now, I only have a couple. These are really simple problems. Okay? Yeah, I don't know if we're going to have a chance to complete them.
Holy shit.
What I'm going to suggest maybe that we do is we'll just jot down the questions and maybe we'll do them tomorrow. Okay? I got two, I think. So jot this down. What is the electric field intensity at a point where a positive charge, 2.4 times 10 to the minus 6 coulombs, experiences a 3.2 Newton force? Okay? I'm hoping you guys are somewhat familiar with scientific notation. Yeah? Okay. The only question will be is how familiar are you on your calculator?
Very.
I guess you should get it.
You'll need a calculator. Yes, a non-phone type calculator.
Yeah, someone will apply. Yeah, just keep it there, so.
Yeah, and it needs to be scientific, right? Because it has to be able to handle scientific notation. So I don't think your phone can probably do that.
My phone.
Mine does.
Does it do it? Okay.
Because we have smartphones.
Oh,
They're
I have a dumb phone.
Oh, that sucks. You got a smart one. Upgrade. It's freezing.
Example number 2, an object to charge 1.0 times 10 to the minus 6 coulombs is in an electric field of 2 times 10 to the 4 newtons per coulomb. What force is applied to the object? This time we're looking for the force. Now, you've already got the formula. Some of you can probably do these already. They're not particularly challenging questions. Okay, I will leave those with you. We will look at them tomorrow, and then I will give you some time to do some questions.
Chance for that.
I don't know.
Don't show it to